Hi, my name is Avery Thomas, and I am a student in Chemistry 1211 at Georgia Tech. In this video, my goal is to explain a little bit about VSEPR theory ideal structure versus quantum mechanical optimization and their application to a specific molecule, nitrogen trifluoride, or NF3. So on the left here, you can see that I have pulled up WebMO, which is what we use to make these representation or model molecules. So as you can see, in the middle we have the central atom is the nitrogen, and then we have the three fluorides surrounding it that are bonded to it. This right here is the VSEPR theory ideal structure, which I will get into, and then on the right there is the same molecule with the nitrogen and then the three fluorides, but it is the quantum mechanics optimization structure, which I will get into a little bit later. So first I will focus on the left. This is the VSEPR theory, so I'll give you a little bit of background information as to what exactly VSEPR theory is. VSEPR theory is a way for chemists to create a 3D representation of a molecule using only its 2D structure combined with our knowledge of how lone pairs behave and affect the molecule structure. So as you can see here, we've got this central atom, but what you don't know is that on this central atom, there are two lone pairs that are supposed to be right here. I will pull up the Lewis structure. So as you can see in this Lewis structure, this actually will show you the two lone pairs, which are right there. And these are what affects the structure of the molecule and gives it its shape, which in this case is a trigonal pyramid. So yeah, that is the molecule according to VSEPR theory. And then on the right, we have the quantum mechanical optimization theory and its structure of the molecule. So to give a little bit of background on that, quantum mechanical optimization takes account of all sorts of things, including the quantization of energy, the wave-length nature of particles, the uncertainty principle, and the correspondence principle, which is a lot of information, but basically quantum mechanics explains the nature of subatomic particles at the smallest scale of energy levels. So you will notice that the molecule has the same shape, but these two little arrows are the first and most visible difference between the two of them. On the VSEPR structure on the left, the dipole arrow, or the dipole moment, which is this little blue thing right here, is much smaller than the dipole moment on the quantum mechanical optimization structure. And this dipole moment, I will pull up some of the actual data right here. You can see that it's numerically supported. The dipole moment within the VSEPR structure right here is 0.11, while the dipole moment for the quantum mechanics structure is 0.492, which is almost 4 or 5 times as great. And then the other main differences, which you can't tell just by looking at them, well, you can tell the bond angles. The bond angles are much smaller in the quantum mechanics model, and then the SCF energy is smaller on the VSEPR structure. So the basic reasoning behind this is that the lone pair has a greater effect on the quantum mechanics model. So the repulsive forces force these fluorine atoms down and causes them to have these smaller bond angles, and that also causes the greater dipole moment and a higher SCF energy. So yeah, that's all because of the repulsive forces. So for that reason, the quantum mechanics model is actually a little bit more accurate, or should I say realistic, in predicting what the nitrogen trifluoride molecule will actually look like. So I hope that sort of helped to break down what VSEPR ideal structures and quantum mechanical optimization structures are, and why and where and how they differ. Okay, thank you for watching.